Question 22 asks us to find the final height of the block after it slides down the ramp and bounces off the spring. We're given a nice diagram and a bunch of values, but one thing we're not given is a spring constant or any sort of measurements for the spring. And so because of that, we're going to assume that this is a perfect spring and all of the energy is conserved. To approach this problem, we can first draw out some of the forces that are acting on the block. So we've got our frictional force, which is going to be opposite the direction of motion. We've got our normal force, which is perpendicular to the surface the block is sitting on. And we've got our force due to gravity, which is going straight down. We also know, while we're not given the height of h, we have a relationship with our d and that angle 30 degrees, and we know that h is just equal to d sine 30, and so our h is 2.5 meters. So getting into this problem, we know that it's going to be a conservation of energy problem, and so we can look at a couple equations that we're going to use here. And so we've got our potential energy due to gravity over here is equal to mass times gravity times that height. The work done is going to be equal to our force times distance. We know our frictional force is equal to our coefficient of kinetic friction times the normal force. And we know that our normal force is equal to mass times gravity times cosine of 30. And the way I found that out is looking over here with this little diagram I drew out with the forces. We can see that we've got our gravitational force in the hypotenuse there, and our normal force is down at the bottom. And so doing a little trig, we can see that our normal force is equal to mass times gravity cosine 30. So we're going to use our conservation of energy at three certain points in this diagram. The first point is going to be at the very top, right before the block is released. Second point is going to be at the bottom when the spring is fully compressed. And the third point is going to be somewhere in the middle here when the block comes back up a certain distance. And so looking at each of those 3 points, we can write out our conservation of energy equations at each of them. To start at the top of the ramp, all we have is potential energy. And so we've got our potential energy due to gravity, and we can call it the initial potential energy due to gravity, is equal to mgh. Then when the spring energy we have more at the bottom of the ramp, that point 2, we're going to have the potential energy in the spring is equal to that initial potential energy due to gravity minus whatever work was done due to friction on the way down. And finally, we've got the potential energy at the top of the rebound. So we're going to have that potential energy due to gravity at the top of the rebound, which we can call the final potential energy due to gravity. And that's going to be equal to the energy that was put back into the block from the spring minus whatever work was done due to friction on the way up. One thing to note is that at each of these 3 points that we've chosen, the block is stationary. It is initially stationary. It is stationary at the very bottom of the ramp when the spring is fully compressed. And it is again stationary when it reaches the apex of its slide back up. And because of that, we don't have to worry about any kinetic energies in our conservation of energy equations. Taking these equations and working them out a little bit, we can start at point 2. And we know that that spring potential energy is equal to the initial gravitational potential energy, which is just mgh, minus the work done by friction on the way down. And we know that work is force times distance. And we know that our frictional force is the coefficient of kinetic friction times our normal force. And so we can write that out as mu sub k times mg cosine of 30 times d. Doing the same thing for point 3, we can work that out a little bit. So we've got our final gravitational potential energy, which we can call mghf, and hf is the value that we're looking for in this problem. And that is equal to our spring potential energy, which we just wrote right here. And so we can grab that. minus the work done by friction on the way up, which is going to equal mu sub k times mg cosine 30. And we'll call that d2, the distance it travels on the way up. So we'll call that first distance d1, and the second distance on the way back up d2. Staying consistent with our terminology, instead of using initials and finals, we'll mark each of our terms with the points they're at. So our first potential energy will be 1, and our third potential energy will be at point 3. Same with the heights. Our final height will be height 3, and our initial height will be height 1. And that should make it a little bit easier to follow as we go through this problem. Now this d2 value here at the end of the equation is currently an unknown. However, we can write it in terms of our final height, h3, using a little bit of trig, because we've got h3 here, and we know that that second distance travel we're calling d2, and we know this angle is still 30 degrees. And so we can write d2 is just equal to our final height divided by sine 30. And with that, we're ready to substitute and simplify. We can cross out mg in each of the terms in this equation, and we can rewrite it as our final height is equal to our initial height minus coefficient of kinetic friction times cosine 30 times that first distance minus our coefficient of kinetic friction cosine 30 times that final distance, which we know is just h3 over sine 30. Now we're left with one equation where the only unknown is our final height, so we just need to rearrange some things and isolate that final height so we can solve for it. So to start, let's move them over to the same side. So we're left with that equation, and then we can divide the left-hand side by our final height, h3, and we're left with 1 minus our coefficient of kinetic friction times cosine 30 over sine 30 is equal to our right-hand side. And we know cosine 30 over sine 30 is just 1 over tan 30. And so we can rearrange again and get that our final height is equal to our initial height minus our coefficient of kinetic friction times cosine 30 times that d1 distance divided by 1 minus our coefficient of kinetic friction over tan 30. Finally, we can plug in some numbers and solve. We've got that our final height is equal to our initial height, which we know is 2.5, minus our coefficient of kinetic friction, which is 0.21, times cosine 30, times that initial height, 5, divided by 1 minus our coefficient of kinetic friction, 0.21, divided by tan 30. And if you take a calculator and you do that whole thing out, you're going to be left with your final height is equal to about 1.17 meters. And that's how you do this one. Hope that helped.